Okay, one last little quick video here on projectile motion. It's gonna be a very short one, but it's a very important topic. It comes up a lot in on the Regents and really in later on physics. So projectile motion is the idea of when you throw something through the air, how it moves, right? So as it flies through the air, important thing that happens is in the x direction, its velocity remains constant, right? Meaning Vx equals whatever it started off at. But in the y direction, it's not constant. It's accelerating. It's accelerating. And in fact, it's accelerating down the whole time. All right, so it's actually behaving like an object that was thrown up in the air and coming back down when it's launched. All right, so the whole time an object flies through the air when being shot, right, its acceleration is equal to negative 9.8 meters per second squared, which we call acceleration due to gravity. The whole time it's in the air, it's doing that. These arrows are representing the acceleration. Its velocity, I'll draw its velocity. Its velocity in the y direction is increasing. That means every second that this object's in the air for, its y velocity is increasing by 9.8 meters per second squared down. All right, x velocity remains constant. So we have all these different questions where we got to figure out how far from the edge of a building something lands. Typically call that delta x or dx. Call this delta y or dy. And we usually use the y direction. We use El Grande in the y direction. 1/2 ay t squared plus v naught y t. Usually that's 0 if it's launched horizontally. It's basically just like it's being dropped. So we use the y direction to figure out the time. Usually we say t equals the square root of 2 delta y over ay. We find the time it takes to hit the ground. And then we go over to the x direction and we figure out how far it goes. Vx doesn't change. So let's look at an example here. Let's say an object is launched horizontally at a speed of 10 meters per second from a height of 10 meters. Okay? Launched horizontally, so Vx is 10 meters per second from a height of 10 meters off the ground. We want to know how long it takes to hit the ground and how far from the edge of the cliff does it land. All right? So typically what we do here is we make two organizational tables. Vx, delta x, and t. We don't need ax because there is no ax. The v initial y, v final y, v average y, acceleration y, change in y, and time. We need all of them over here because we don't know, because it's accelerating. So 10 meters per second, that's our Vx. Delta x we don't know, t we don't know. VIY, launched horizontally, so you know that's 0 meters per second. V final y we don't know, v average y we don't know. Acceleration y we know is negative 9.8 meters per second squared. You could make this positive if you say down is positive. And if you make that positive, then you need to make delta y positive. If I make ay negative, I have to make delta y negative to be consistent. I'm saying down is negative. So delta y is negative 10 meters. All right, so to get delta x, it's El Grande, right? It's 1/2 ax t squared plus v naught x t, or v initial xt. This term disappears because the acceleration in y direction is 0. So delta x equals v initial x times t. Well, cool, I got v initial x, but I don't have t. So now we go to the y direction. Delta y equals 1/2 ay t squared plus v initial yt. All right, v initial yt. That term goes to 0 because it's launched horizontally. There is no initial y component of velocity. So delta y is negative 10. I'm not going to put the numbers in because I already wrote them in the organizational table. Man, I'm gonna be lazy here. I'm going to round that to 10. Negative 10 meters per second squared times t squared. Boom, boom. 2 equals t squared. Radical 2. T equals radical 2, or 1.4 seconds. That's a good one to remember. When something is dropped from 10 meters, it always takes 1.4 seconds to hit the ground as long as air resistance is negligible. I should have mentioned that. Air resistance is negligible in all these problems. So we do this, 10 times that equals delta x equals 14 meters. 10 meters per second is pretty fast. So, you know, landing 14 meters from the edge of the cliff is reasonable. A couple other things to note here. That's the basic calculation you always have to do. But then just remember, I said this in the beginning, but the other thing they love to ask is when it's launched into the air, to, you know, draw its acceleration vector. Remember, it's always accelerating down. All right. If there was air drag, and the optimal launch angle is 45 degrees to get the maximum range. I'm not going to go through that proof now. If there's air drag, it turns out the trajectory looks more like that, which some of you probably know from golf or baseball or football. Anyhow, that's about it for projectile motion. Take a look. I don't think there's really anything else in that chapter. It does go through break and velocity vectors into components, so take a look at that. Next up will be circular motion. All right, guys, take it easy.